So I'm going to talk about how to move fast and not break things, building a data platform that will scale with your organization. Cool. So first, a little background context about me and the company that I work with. So my name's Elijah. I'm the co-creator of Hamilton, as Tristan said. Hamilton was released in 2021. I'll tell you a little bit more about it soon. I'm the CTO and co-founder of DAGWorks. We just spun off and started a company based off of Hamilton, graduated YC a year and a half ago, and we've been building ever since. And I've spent my entire career in machine learning and data platforms. So I started off studying where sort of the interaction of math and computer science, and found that I was really interested in building tools that expose compute to people who have a really mathematical brain. So there's a lot of people who have a technical mindset, and a lot of people who have a very quantitative mindset. And my interest was sort of putting those together and seeing what would happen. So I joined TwoSigma after I graduated school, where I built production trading models and plug-and-play pieces of them for quants. Then I joined Stitch Fix, where my co-founder and I built out a machine learning platform that over 100 data scientists used. Every model that was deployed in Stitch Fix was deployed through our machine learning platform. Sort of a really fun thing. We wrote a lot of blog posts. You can search my name or search Stitch Fix machine learning, and you'll probably find it. And then we also created a product called Hamilton. We then spun off and created DAGWorks, the company that I'm working for now, from that product, and here I am. So, a little bit about DAGWorks. Our goal is to standardize data, machine learning, and LLM pipelines. And we are open core, meaning that we have some closed source stuff that we sell, but that's not what I'm going to be talking about at all in this talk. I'm not going to be selling you anything. I'm just going to be talking about open source stuff that you can download from the internet and play with whenever you want. So today, these are the 4 take-homes. If you're really good at just like synthesizing an idea, then you can probably doze off after this slide. But the things I want to convince you are that 1, there's a trade-off between building quickly and building reliably. This should all be a pretty natural thing to you if you've been building for some time. 2, having a good platform can make it less of a trade-off. 3, Hamilton, the open source product that we built, is a good conduit to do so, and I'll sort of walk you through a few different ways in which you can use Hamilton that'll help you with that. And 4, that Hamilton can help you move quickly from dev to prod and back to dev for iteration, right? So that it can work both for that 0 to 1 and for 1 to 100. So, how I'm going to show that to you, here's the agenda. 1, I'm going to talk about a mental, really a quantitative model for thinking about this trade-off that comes from my quantitative finance days. 2, I'll talk about how platforms can sort of help change that model or help you interact with it. 3, I'll talk about how Hamilton can form a lightweight platform abstraction, a standardization that can sort of implement that model and be the platform. I'll walk through a few different ways in which you can use Hamilton. Then I'll talk about some applications. All right, so this is why I mentioned machine learning models and GPT-4, because I'm going to be talking about how you can use Hamilton for a standard machine learning like classical ML case, and how you can use it for LLM, retrieval augmented generation. Then we'll be zooming out and looking a little bit about what the future looks like. There's going to be some code in this talk. I'll try to explain it. If you have questions or something's confusing, I'll be around afterwards to explain. If you want to just look at the code and doze off, there'll be other points too. So, how do I think about these trade-offs? Well, a question for all of you. Does anybody know what these pictures are? If anybody wants to say. Anyone tell me the one on the left? On my left? What's that? Yeah, so it's Formula 1, right? Yep. And the other one? Anybody? What's that? Yeah, it's a drag race, right? So what describes your ML and AI code? Just abstractly, not sort of, there's no right answer to this. And I think people probably think there should be a right answer. But if your code is more like a drag race, raise your hand. Cool. And if your code is more like a Formula 1 race, raise your hand. Cool. So the difference here is that drag racing is about the fastest way to get from point A to point B. A Formula 1 race is highly tuned and goes in a circle again and again and again, right? They're much longer. So looking at how this works in the data science and ML world and AI, there's an interesting thing when I talk to data scientists. There's sort of this like impressive cognitive dissonance they're capable of, right? And I've heard these two things uttered basically in the same breath. One, I must quickly deliver above all else, meaning that the most important thing is getting something out to production. There's your drag race. And two, there's way too much technical debt to do my job, right? So must deliver above all else. Start building stuff, get your notebook out, ship your notebook in whatever like notebook to prod thing you've got, save a model somewhere, good, your model's in production serving customers. Keep doing that, 60,000 lines of code later, 8 production outages, 30 terabytes of unstructured data floating around that you have no idea what to do with, but costs you a lot of money to hold, and a ginormous snowflake bill leaves you with too much tech debt to do your job. So the next time you want to get that model from 1 to 100, really optimize, iterate, and take it to the next level, you're stuck dealing with the model you just built, right? And this is sort of an interesting dilemma and forms the core trade-off that we're going to be talking about. And I like to sort of represent it with this meme, where the idea is the limiting resource is time and energy, right? Because everybody's limited by time and energy. And you can only pick 2 of these, right? You can choose to add value to your organization, bring in revenue. You can choose to move quickly, meaning you get it from 0 to 1 as quickly as possible, and you can choose to build reliably. So if you have to pick 2, I think that we would all choose add value as the first one, right? Because if you don't add value, you're probably going to get fired. So now it's a pick one between the 2 of them, and you're stuck somewhere on the spectrum of moving quickly and building reliably. So I think about this as my quantitative model for this, it comes from the world of quantitative finance, where you're building out portfolios, right? And you're choosing sort of things, you're optimizing between risk and reward. You can either have a risk-free portfolio or you can either have a risky, highly rewarding portfolio or an entirely risk-free, low-reward portfolio, and you've got to choose something. In this case, we're choosing between moving fast and building reliably, right? And that curve is the optimal set of points where you're given some amount of quick moving you have, you're moving as reliably as you can be, and vice versa, right? So you can just ship the notebook, that's moving fast, you did your EDA, you're done, ship it to production, great. You can build decently structured code, copy your notebook, refactor it into a few different functions, you're good to go. Or you can build configurable, reusable, and well-documented components, right? That's going to take a lot longer, but it's going to be easier to debug, easier to understand, and easier to pass off. This is called, that space is called the efficient frontier, quantitative finance. In more mathy terms, this is called an isoquant curve. What it's called doesn't really matter, but just remember that there's the shape of this curve, and this represents the trade-off. So we now have established the problem that there's a trade-off between building quickly and building reliably. And I'm going to talk about how building a platform can help you sort of ameliorate that trade-off, make it easier to deal with. So what are the strategic goals of the platform, and how do they relate to this curve? Well, it's threefold. One, we want to make it easy to operate on that curve, so that you're not operating inside it, but you're operating on the most efficient place possible on that curve, right? This involves teaching and building tools to make it so that you can operate efficiently. Two, we actually want to change the shape of that curve. So we want to make it so it's now more possible to operate more efficiently, given how reliably you can operate. And three, we want to make it easy to move along the curve. Move from dev on the upper left of that curve to prod and back. So make it easy to operate on the curve. We're looking at moving from the inside of the curve to the efficient frontier, making everybody more efficient. Two, change the shape of the curve. We actually want to make it more of a right angle, right? Because if it's a pure right angle, then there is no trade-off. There's always going to be a trade-off, but a little more right angle is going to make everybody happier. And three, we want to make it easy to move along the curve, right? So easy to move from your drag race to Formula One, and then back to a drag race the next time you want to make a big change to the system. It shouldn't have to be a choice between it, and it should be pretty easy to move depending on what you need to do at the time. So that's sort of the way that I think about building a platform, and my whole career has been building platforms. The one that I'm most excited about is Hamilton, which is sort of a lightweight platform abstraction. So you can use it to build a platform in your data team. It forms a platform in itself, and it can plug into a lot of things. All right, so first, as I said earlier, this is all open source. You can get started in 15 minutes. There's a bunch of documentation we have. You can actually try it out online at tryhamilton.dev. They were running Python in the browser, which is like a super cool new thing you can do these days, where you can run it, see the DAG, mess around with it, add different nodes, and just like have some fun. This is where we go to show people Hamilton first. Right, we have some users here. So we've got we've got a decent amount of traction that we're super excited about. It started at Stitch Fix. The British cycling team is using it. We've got teams at Coinbase, at AWS. I mean, they're all bringing it to like make their data platform teams more efficient. These are just sort of a small group of people. We really don't know who's using it fully in the wild. We have some sense of it, but these are really the people that come to us and want to talk to us and tell us about their cases. So Hamilton comes from one like really simple idea. And the idea was, what if every asset that we have corresponded to exactly one Python function? So if you went to Pete's talk on Dagster, I think it was yesterday, you'll start seeing that there are some like similar philosophical elements. So what if every asset that you have corresponded to exactly one Python function? And what if the way that function was written told you everything you needed to know about your data pipeline, right? So in Hamilton, the artifact that you can get, asset, is determined by the name of the function. The dependencies are determined by the parameters. So again, this is very comparable to other frameworks. If you've seen PyTest, this is the exact same thing as PyTest fixtures. And Dagster software-defined assets, which came out a little bit after Hamilton, also use this sort of exact same pattern. So what does this look like compared to code you might be familiar with? Data frames and series are kind of like the bread and butter that a lot of people speak of. It doesn't have to be data frames and series. It can be any Python object. But a nice way to demonstrate it is looking at sort of a data frame transform. So instead of saying this item in your data frame is equal to this item plus another item, and then this item is some transformation, you define them each as functions, right? So instead of dfc equals dfa plus dfb, dfd equals transform dfc, you declare a function for each asset that you want, right? C is a function of A and B, and D is a function of C. The outputs correspond to the function name. So now we have outputs C and D, and the inputs correspond to the function arguments. So these inputs can refer either to upstream functions or to other inputs that you need to pass in from the outside world. For the full hello world, as to how you tie this together, you define your functions, you put them in a module, and then this driver says what and when to execute, right? So you instantiate your driver, you can pass it some data, and you tell it what it needs to execute, and it's smart enough to just run the pieces that you want, and to just give you the assets you need. So to hammer this all home, the TLDR, for each transform you write a function. Functions declare a DAG, a directed acyclic graph, a flowchart, whatever you want to call it, something that looks like that. D depends on C, C depends on A, and C depends on B. And Hamilton handles DAG execution with the driver. So the thing you might be wondering if you started looking at that code is you're like, wait, now we've got functions when we had variable assignments before. Isn't that more verbose? What if I want to do like a big old for loop and go over and do it a bunch of times? I want to say verbosity is not always a bad thing. Code is read much more often than it's written, and verbosity can lend itself to very sort of good code readability. But when it is, we have something that we call decorators. And these are sort of like high-level operators on top of these functions that can do stuff like attaching metadata to it, currying and repeating a function invocation, take one data frame and turn it into multiple series, do data validation, I'll show you this later in the talk, do sort of conditional transformations, so do a static input that sort of determines how the DAG is shaped, and then recursively utilize groups of nodes so you can have DAGs within DAGs, because, yeah, Doug, I heard you like DAGs. All right, so what sort of, like, how does this sort of map to your data workflow, and what are sort of the properties you get from this? Like, how does this make your life easier? Well, a few different areas. Testing, scaling, caching, data quality, and integrations, sort of integration with external infrastructure and on your own infrastructure, all get easier when you've abstracted things out into functions, right? So testing. This is simple, because everything is a Python function. It implies easy testing, because testing requires sort of well-contained and modular code, and that's just naturally going to be the case with Hamilton, which allows faster development, right? So helping you move quickly along the curve to sort of develop and iterate, and to help you sort of live along the curve so you can build easier tests and operate more reliably. So what does this look like? This is just a very simple example of unit tests. On the top, there's a function that does some like very data sciencey thing, like I want to get the height, zero mean the unit variant, like zero mean with unit variance, and it takes in previous things. And on the bottom, it's just a PyTest, right? This should be fairly familiar to most people who've done testing before. But the point is, because it's a function, you can easily get these nice testable properties. And integration testing. This is really cool. Integration testing has a million meanings. So I've seen it anything from running 2 functions together to running an entire system. And this one is something that I've internally called pathway testing. I don't think anybody else uses that term. But the idea is you can run one portion of the DAG. So if A is a data set and B is sort of an input, you can pass in a smaller data set to run an integration test of the whole thing, have that run quickly, and then also run it in production. Hamilton doesn't care how you run it, but it has tools to allow you to sort of like inject data in and short circuit pieces of the DAG, right? So you can inject sample data or screw it, highlight A in red and just run on sample data, or run on prod data if you want to see what happens. All right, scaling. So the driver handles where to run, and it can also delegate down to sort of whatever Python framework you want. So pandas, ibis, you can work with Lance, as Changxi was talking about before. Spark, like whatever you want. Hamilton doesn't care, it's just a way of organizing these functions. So you can scale up with parallelism, and the Hamilton has a few simple constructs to abstract away parallelism, and delegate. You can choose sort of an executor to run these parallel functions, and you can delegate to underlying frameworks. So I'm going to talk about the parallelism piece, which is how to use Hamilton to build highly parallel code, and it's pretty simple. So you do this map, so it's kind of like a very simple map reduce operation. So if you declare a function output as this parallelizable type, it tells us that everything beyond that is going to be run as many times as you have outputs for that parallelizable. It uses a yield, so for every yield, you run a new sort of like sub-DAG. In the reduce step, that's sort of later on, that forms the end of that sub-DAG, right? So between parallelizable and a collect statement, which is declared as the input, everything there is run n amounts of times. You map them out and reduce them back. And then you can delegate to a custom or built-in executor. So the cool thing is you can move from a synchronous executor, which will run one after the other for 3 sort of cases if you're running locally, to something that scales up and runs on Ray or Dask or Modal, whatever you want. You can see here, I've got, this is like one of the examples I've got, which is city data that leads to a bunch of different DAGs that all leads to statistics by each of those cities. This is a Kaggle competition, I think. So, caching. How does Hamilton make it easy to cache? The problem here being you train an expensive model, you run it all the way through, then you have one sort of like null pointer exception later on, and you have to retrain the whole thing. This is often done in development. So how can this make it, how can we use Hamilton to do caching? Well, we have a single line extension that'll add caching to your workflow. So in this case, we have this is using the driver builder API, which is sort of a modular way of putting together drivers. We have this notion of fingerprinting, which is caching the combination of inputs, data, and code, all with a one-line change. Right now, this is all sort of pluggable and composable, so you can build whatever you want on top of this. But right now, it's a speed up for development, so you can run it locally. We also have ideas about how to put it into sort of running on a distributed system or running on a database, so come to us and chat if you're interested. But all you have to do is add one of the sort of graph adapters, which will load it from cache if it needs to and short circuit the prior computation of the DAG if everything is well aligned and matches. If you make a change, though, it'll rerun just the parts it needs. We're hoping that this saves people time in dev, and we've started to see that be the case. All right, data quality. This is sort of making you be able to be more efficient, so you can be both more reliable. A system where you know data quality and have observability into it is naturally going to be more reliable and allow you to move faster. And it's really easy to add, so it helps you move from dev to production and back. This is simple. This is just another decorator. I alluded to it earlier. In this case, we're just checking the output. We should probably check that the mean is 0 here. But we're just really checking, okay, is the data point a NumPy float 64? The range is between -5 and 5. And do we allow any nulls in this? This has sort of configurable ways it can run. It can log a warning. It can fail, whatever you want. But it's just a one-line addition, and you can customize it as much as you want. So there's an integration we have with Pandera that allows you to run a Pandera check on the output of a function, so you can assert that it matches a schema, and you can build your own custom one. So we have a checkoutput.custom that just takes in a class. This is a one-line change. You can develop all your code and then add this in after the fact. And integrations. How do you customize execution with Hamilton? Well, there's a lot that I could talk about here. We have a very like plugin friendly philosophy. It's almost too plugin friendly because people ask us how to do something, and we'll say like, oh, you can like implement one of these 18 classes that'll do exactly the thing you want. But the plus side of that is you can do anything you want with it. You can run on any infrastructure, delegate to whatever you want, and plug in any library that you need. In this case, there are sort of two things I'm going to talk about. There's something called a lifecycle method. So we have all sorts of points in the lifecycle that we can delegate out to a class that you implement and pass in that says how to run the DAG, right? So you can run something before a node executes and after a node executes. We did this to add in sort of distributed tracing and telemetry. So you could like, we have stuff that logs to Datadog before and after. In this case, we're overriding how a node executes and using this really cool feature of Python I discovered recently called pdb.runCall. So I've always loved the PDB debugger. Also, this is like the coolest hack if you want to know how to, many of you probably know this, but if you're just like debugging code in Python, if you stick in pdb.setTrace, it'll pause execution and give you an interactive shell. pdb.runCall actually goes one step further. It'll pause execution at the first line of the function you call, passing in the arguments, so you can pretend you're in a Jupyter notebook while you're running code in development or prod, right? And this is a really good way to like get into a function and see what happens. So the cool thing is by just implementing this, you can stop before every single node. The real one that we have in the library has like configures which nodes it stops before. So you can say like, oh, this is the problematic node, I want to stop there. But this allows you to say like, oh, this point is behaving weirdly. I want to see what happens when I get there. What does the data look like? You can pause, you can do whatever you want. You can even write it out to a file, like who knows what, choice is yours. But this is calling out to that. And it's just like one line of code, a few lines of code to write it and one line of code to add it in. And we have a tool called materializers. I realize this is actually a lot of code, but the high level is that on the left, we have a class that tells how to save data to MLflow, right? So if you're saving a model, the last step is going to be saving a model to MLflow. You might want to save it also to S3, like you don't really care where the model, like you might have multiple directions you want to save the model in. This might be very custom to the way you do it, so you might want to expose different parameters, but on the left is a class that can be used to save to MLflow, right? So it defines like how do we save data, how do you refer to this, and on the right is how we call it, right? So in this case, we have the driver before. Instead of calling execute, as I showed earlier, we call materialize to .sklearn MLflow. It should probably just be MLflow, and pass it the data it needs so it knows what to materialize, so that that DAG adds a materialization step at the end of execution, which does the saving for you, right? So this is a way to do we also have a loader too, so you can separate out the extraction and the load from the transformation step entirely. There's also tools to put this inside the DAG if you want, like inside the function, sort of with equivalent APIs. But this is a nice way to sort of attach where the data is to how it's being invoked, and you can even call it in staging and prod with sort of different places you want to save it. There's a ton of materializers. I think we did like the open source October. I don't remember, like Hacktober, I guess. Yeah, we did Hacktober. And we had like hundreds of contributions of people doing different materializers. So the odds are there's something you can do and you can customize it fully. All right. So how do you use Hamilton in a production use case? Well, let's talk about both the training and building your own models and the call out to GPT-4 cases. Both are very valid and common these days. I think the world is kind of deciding where it wants to live and like which cases go to which, but Hamilton is future-proof in that way, applicable towards both. So, machine learning pipelines. This is the classical ML case. I've been doing this for quite a bit. And it's pretty simple. All you do is define a machine learning pipeline in Hamilton where each step is a function. Note, the granularity of this is entirely up to you. So you can have one function that does the data loading in this case. You can load the data and clean it in a separate one. I don't really care how you use it, as long as it's broken into sort of like nice, clean functions. In this case, the final thing we have is inference, predicted digits. It takes in the model that we train. We then have a model, which is like a very simple support vector model. And then it takes in the digits data, right? So you can kind of like trace back, figure out exactly the lineage through. And what it looks like is a very simple DAG like this. So you go from your digits data to your digits model to to predicted digits. And this is a machine learning pipeline. And how does this work in practice? Well, machine learning engineers, data scientists will write machine learning pipelines as Hamilton steps, right? So just as we showed you above, then they can easily add data quality. So you can check before you train the model whether there's sort of a base set of assumptions are made, so you can shift left and push the error earlier. You then scale up by delegating to Spark, Ray, and Dask. I didn't show you how to sort of like, we have some tools that allow you to move between APIs, depending on how you instantiate the driver. I didn't really show that, but there are ways to delegate out to other executors. You can then separate the code structure from the task structure. So this is really cool. It's like, if you're building on Airflow, then your code is naturally going to become focused on how data is loaded into Airflow and how it's loaded out, and that's going to be brittle, right? You're going to be thinking about tasks, but you really should be thinking about the data you need, and the tasks are almost a secondary concern. Hamilton allows you to break up the pieces, run some on one Airflow task, some on another Airflow task. If you want to go over to use Prefect or Dagster, that's totally fine. Run it there. It makes it sort of nice and portable. You can then test locally on sample data, even have a unit test that runs a really small model on your sample data just to make sure the basics of the code works, and scale up and run remotely on your full data on your super beefy machine in production when you have a schedule and you're happy to wait a few hours. Then, using the materializes we showed before, you can integrate a model registry or other providers. There's all sorts of different ways to plug it in. The cool thing is, with this sort of materializer capability or with all these plugins, a data team that has a few data scientists, MLEs, all working on models, can sort of like get together and decide their favorite ways to save it, favorite ways to save data, favorite ways to load data, and favorite ways to observe and track the process. And they can make those common libraries, which will help make everybody faster. So going back to that curve, right? This makes it easy to move into production, to sort of move along that curve, because you can make common the different ways you do stuff and access them without sort of burying them deep into your code. It also can make you more efficient, because now you can sort of like build a platform easily with these sort of common abstractions that you couldn't have done before. All right, what does the LLM and RAG case look like? To be fair, this is actually, I think, like not super well defined these days, so I'm going to go in one specific piece of it. But there are a million different use cases we've seen of people sort of going out to Hamilton to model this. Here is a DAG. This is a bit more complicated, but the thing to note are there are the like double line ones. So one's called chunks tests, and one's called summarized chunks. Zooming in on them there. The chunk text outputs a bunch of different chunks. Summarized chunk goes to OpenAI and does some sort of summarization. It might even stick it in the vector database, up to what we want. And the summarized chunk joins them all together, right? So simple MapReduce, go hit the OpenAI API for each version, run them all on your designated executor, and then join them all together to form all the chunks. Here's what it looks like. In this case, we're doing our tokenizer, chunking up everything, running through each chunk, yielding it, creating it. Remember, it returns parallelizable, the idea that Hamilton can then run that in parallel. Then we do our summarization there. This is delightfully simple. It just does a summarization thing. I think we have a prompt that we declare from an external place, so we have sort of that like nice inversion. Then we run it through the OpenAI API. This could use LangChain. This could use whatever you want. Up to you. And then we summarize the chunk. This just does a quote.join, simplest join possible, but it gets it in as this collect operation, which is going to be a list. Right? So go from your chunks, using Hamilton, delegate to whatever executor you want, run each one as an API request, and the executor has the capability of sort of like rate limiting it or throttling it if you want, and then go back and summarize the chunks, joining them all together. Right? So if this was too much in detail for you, the high level is that Hamilton abstracts away the organization of it and the way that it's run. So all you have to do is focus on the one little piece that you're thinking about at the time. You can unit test that, and you can run it bit by bit, run it locally, and then run it in prod super easily. All right. So yeah, so what does this look like? To drive it home, write a simple Hamilton pipeline, in this case chunk, summarize, join in this case, but you could also have like a query section. Leverage that tool Parallelizable for dynamic execution. Test locally on a small data set in a synchronous mode. So the nice thing is you can run sort of on a small data set, run on 2 of them, make sure your code actually works, run it one after the other, and then scale up, abstracting, and then scale up in production or for your sort of bigger test data set when you're doing analysis. Then using all of these materializers and other capabilities, you can hook into eval frameworks. So you can have after every node, save to some eval framework, log to some observability tool, whatever you want. Hamilton allows you to plug it in. All right, so that is the meat of the talk. Again, I'll be around afterwards to answer any questions in case that wasn't clear. But let's zoom out and look at sort of what we talked about and where we want to go next. All right, so at a high level, there will always be a trade-off, right? You can choose to either build 100% reliably, which is impossible, but build close to 100% reliably, or move super fast. And it's up to you where you want to live along that. That trade-off forms like the core of the data science quant, AI researcher, MLE, et cetera, dilemma. And most people I've seen have dealt with that in some way or another. A platform with a nice abstraction can make that a lot less painful, right? So platforms can inject and guide best practices. They can build common tools that allow it, sort of the team to be greater than the sum of its parts, and they can help you change the shape of that curve, right? Hamilton has lots of hooks to enable you to scale. So you get these good software practices for free, testing, documentation I didn't talk about, but each function to sort of like forms its own documentation and documents the structure, modularity, sort of organization to modules, et cetera. Then you can move along the curve, right? There are all these like little one-line additions that'll add production quality concerns in, such as data quality, right? And then you can scale up from a startup to an enterprise, moving along that curve with less of a trade-off and with minimal code changes, right? Really enabling you to go from your initial Jupyter notebook, take each cell, stick it into a function, you've got a production-ready pipeline, then as you keep running it and it breaks, add more and more pieces, and now you have both move fast and built reliably. All right, so taking a big step back, I want to say this is almost a new approach to data. So this new approach to data is asset-based, right? You're thinking about what you want, not how to compute it, because you're fully decoupled, right? You specify what you want in functions, the functions that you query and the functions that you execute, and you don't think about how to compute it until later, until you're actually running those functions. I think this is a pattern that has shown up everywhere, right? We've just moved it sort of higher and higher up the stack. If you think about Spark, if you think about IBIS, all of these tools are making it that you sort of, like functional programming even, are making it that you specify less about how to compute things and more about what you want, and the system is smart. The difference between Hamilton, though, sort of the novel way it does it, is it allows you full visibility into any level of the stack that you want. This new approach to data is declarative. You don't want to split the way you think between how it works and where it's called, right? A similar point. You just declare what you want, and the same code can model both, right? So as compared to like an imperative or procedural approach to data modeling, you have the how and the where married together. So every function knows exactly, every data asset knows exactly where it's coming from. You can tell where it's used, so that if you need to go from production data to the code that generated it, that's a one-step hop, right? And portable. Data flows should be able to run anywhere. Oftentimes, people find themselves running the same code in batch and online. The feature engineering case is a very common one here, where you want to run sort of the same stuff, scale it up over a massive data set on Spark, doing a map operation, and then you want to run it online in a microservice as well. That's a hard problem. Hamilton helps you solve it by allowing this code, this just Python code, to be portable and not care about the infrastructure. It can kind of run anywhere. Actually, there's another talk that I have that goes very much into depth about how you might do that, and making it easier to migrate, right? As data scientists, as quants, as AI researchers, whatever you are, you shouldn't be thinking too much about the infrastructure that it's running on, unless you need to, right? If you're dealing with GPUs, if you're dealing with sort of large data, you're gonna start thinking about that. But you should be able to build code that can run anywhere, that you can move from system to system, so that when your platform team comes and they're like, oh, I want to move from Airflow to Dagster, for you that's a very easy thing, right? You don't have to have thought about all the different APIs you use and how you model your code around the infrastructure. Instead, you can think about how you model the code in general, and it can apply towards any infrastructure. So we have all sorts of exciting things we're working on. I'm happy to tell you more about it afterwards, but for now, I really appreciate you coming to my talk. Thank you so much.